that finally brings us, once I manage to scroll this up over here, okay. Finally, we can define a tangent cone. The tangent cone, what do you think would, how would you define it? You've got all of these tangents, now what should we do? The set of all tangents is going to define a tangent cone, okay. Set of all tangents to sigma at a feasible point x, okay, is called the tangent cone, and the notation for it is this, okay. So it has everything that we need in it. It has the feasible set is in it, the point x is in it, and it's a collection of all of these all the tangents that are being derived from the feasible sequence. So this is my tangent cone, okay. So for the problem that we have been talking about, how will you define the tangent cone? We have two sequences, right? We had the blue arrow and we had the pink arrow. So if you were to define, give me a precise definition of this tangent cone. So at point A, we have what would it be? It could either be the up arrow or it could be the down arrow. Any sequence I take is going to give me either of these two arrows. So how do I capture this? If I were to parameterize this, I could simply write this as this. This captures plus minus, right? Now you are thinking of unit vectors. Some of you are thinking of unit vectors. Why is this 0 d2 and not 0 plus minus 1? If I had defined, so it depends on how you define your sequence over here, right? This scalar sequence Tk, the scalar sequence Tk, if it was the L2 norm of Zk minus x, then the tangent vector that I get, the either the blue or the pink arrow, is going to have magnitude 1. Now supposing I decide to choose Tk as equal to 100 times Zk minus x, 100 times the norm of this, it satisfies the definition because it tends to 0, or instead of 100, 1 by 100, whatever, it's still a tangent, right? And what is the definition of the tangent cone? The set of all possible tangents. So that's why I could have magnitude 1, I could have magnitude 100, 1 by 100, whatever I want, rational, irrational, whatever. So that's why when I put all of these guys together, I get a tangent cone which is like the way I've defined it over here. It's not a vector space, it's a cone. A cone is a cone a vector space? Is a cone a vector space? Because so if I'm exactly, so we'll come to this a little bit later, the way I define a cone, right? If an element lives in the cone, then a positive scalar times that vector should also be in that set. But if I put negative, I'm out of it, right? So it's not a vector space in that sense. But idea is similar. So right. I think one thing I forgot to mention over here, this feasible, obviously this is tied to the definition of a cone. This scalar should be positive, so that the flipping of sign does not happen. Yeah. Well, okay. So let me come to the definition of the cone. I'll revise the definition of the cone, and that should make it clear. Okay. So far the definition of tangent cone is at least clear. So how do we do it? Start with feasible sequence. Feasible sequence is fine. Then I define another scalar to help me to get a limiting direction of a feasible sequence. That gives me a tangent. The set of all tangents gives me a tangent cone. If you look back at your notes, when we defined the set of linearized feasible directions, did I get the same set 0 comma d2? Yes, when I defined the constraint in the normal way as x1 squared plus x2 squared minus 2, and I did the linearized feasible directions, that's exactly the set that I got. So there's an agreement there between algebra and geometry over here. But when I squared the constraint, I got algebra said any direction is possible, and geometry said geometry is going to be unchanged. Why? Because I can square the constraint, my feasible sequence will still remain the same. It has to be on the circle. Whether I square it, cube it, whatever, the feasible sequence, I mean the feasible set will remain the same. So that way, this definition of tangent cone is immune to all of these funny tricks that I do with algebra, right? So this is what we needed to arrive at, okay. Now there are some questions about cone, so let's talk about cone as an aside. So we say okay, that's the definition of a cone. So it's a set M such that for every x that belongs to that set, alpha times M also belongs to that same set. Sorry, this should be alpha times x also belongs to M, and alpha should be positive, right? So you can take two examples very quickly. For example, x1, x2, so I'm talking two-dimensional plane, okay. Supposing I say x1 greater than 0 and x2 greater than 0. So if I were to sketch this, what does this look like? First quadrant, right? So I'm basically saying this region. So what are we saying? Pick some point over here. If I multiply this by 2.75, will it still be in the pink region? It would be, it will just be like this, right? Can I multiply it by -1? That's not allowed as per the definition of the cone, right? So this is a cone for sure because it obviously satisfies the definition over here. We can further qualify this. Is there some special property you can infer in this cone? Can we talk about convexity? Is this a convex set? The linear combination, if I take any 2 points, does it live in the same set? Yes. So this is actually an example of a convex cone, the pink region. Okay. Let's just to make sure that you don't get the idea that all cones are always convex, let's take another example. I'm going to define a new set like this. So x1 greater than equal to 0. So x1 greater than equal to 0 is going to be which region? The right half plane, right? It's going to be this. And x2 greater than equal to 0 is going to be what? It's going to be the upper half plane. And do I have an AND or a OR condition? OR condition. Therefore, what is the set? This quadrant number 1, 2 and 4. Third quadrant is gone, right? So now you can see that if I take some vector, let us say I take a vector over here. This belongs to the set. Does 2 times this belong to the set? Right? You can see, take any positive scalar, it will live in this. In this particular example of the blue arrow, if I do -2, will it work? It works, but let's not push our luck, because if I take a vector like this, then that -2 will not work. Okay, so this is an example of a non-convex cone. Okay. So now, having revised what we mean by cone, let's answer the question that why did we call this thing why is the tangent cone a cone? Why is it a cone? Okay. So we just have to use the definition of a cone. Okay. So say that some vector d belongs to the set T. This is a cone. Okay. Then we have to ask, does alpha times d also live in the same? That's the question. Okay. So remember, d was given as the limiting direction, k tends to infinity, x minus, sorry, not x minus zk, zk minus x divided by tk. This is the definition of the tangent. How do you think we can prove this statement? He has the right answer. Remember, the only property of tk was what? Tk should tend to 0 for large k. That's the only property of tk that we cared about. So if I, instead of using this tk, supposing I define a tk dash is equal to tk by alpha, still fine, right? And if I define it as tk by alpha, the vector that I get will be alpha times d, and therefore this also is, this is the same vector, but I just changed my definition of tk. So along with the fact that tk is greater than 0, you can see that this object that we have defined is a cone. In a few moments, we will start doing some further geometry with this, which will convince you that this is a cone. I will draw some diagrams, but at least if you go from the dry algebraic definition, you can see that this is a cone, because take a vector, its multiple is also in it. That multiple, the freedom to choose that multiple comes from the fact of the freedom in defining my tk. Yeah. At a point. No, we just did that, right? So for example, if you look back here, where did my famous diagram go? Yeah, at that same point over here, I was able to define at least 2 sequences, and therefore at least 2 tangents. I have a sequence zk, I have a sequence wk. Correct. So in this case, so but you agree that I have multiple tangents. I have multiple tangents, and the tangent cone in this case is an entire line. Yeah. I mean, in 2D, there's not much more I can visualize. If this were, for example, a sphere, then the tangent cone would be like an entire plane. You can think of it like this, and then it will get more and more complicated. But in 2D, this is about maximum I could do. Yeah, don't forget Cornetto for now. I mean, yeah. So just keep this, the definition of cone that we said over here, right? This is what you have to keep in mind. If an element belongs to that set and it's positive multiple, then you call that set a cone. So now it's not a vector space, right? What is the, how would I define a vector space? That any linear combination of the basis elements will also live in the same space, including the origin. But here every linear combination is not allowed. I am only allowing you to take positive combinations. Hmm. Yeah, so you can come up with pathological examples like that, which in which case it turns out to be, it will be like a one-dimensional vector space, right? So what I defined over here, 0 comma d2, d2 lives in all R. This is, you can think of this as a one-dimensional vector space, but this is by chance. We cannot make a claim that this is a vector space. It's a, no, the tangent cone idea is valid for any constraint. Here we have taken this example. That would be the exterior of the thing, interior of the circle, right? Yeah. There will be multiple feasible. Correct. Yeah. So you will get a whole bunch of different tangents, right? Idea will still remain the same. but then you are violating the basic definition of a feasible sequence. Property B, if it oscillates, it tends to the point you are saying, but it oscillates about the point, right. So then in that case, so in that case the definition of the tangent is a little problematic, right, because yeah. So what I would do then is I would split that sequence into two sequences, keep all those points that are staying on one side of the point to be sequence 1, sequence 2, then I can define two tangents, and then putting it together I can define a tangent cone. If you're talking about points living in the interior, then there is no oscillation, it's all on one side, no? Mm. It oscillates like this, it reaches X, but then whether it reaches X from down or from up. Correct, so that's what I'm saying. In that case, I would split the sequence definition such that I get one part that has kind of monotonic behavior. Then from each of those, I can define a tangent direction and then put it together. Finally, I'm putting it all together in the tangent cone. That's what I care about. So may as well make my life simpler. Right. Okay, so we have reached all the way to tangent cone. Okay. Now comes the part where I link the whole idea of tangent cones and algebra. Okay, so let's note that down over here. So we have a new definition. So this is called LICQ. Remember in the previous section I had mentioned that there is something called constraint qualification that we have to do. So this is that constraint qualification which is called LICQ, which is linear independence constraint qualification. What does this say? So it says, it's a little bit of a long definition, let's write it down. So given a feasible point X, okay, and the active constraint set AX. Remember, what does the active constraint set consist of? Equalities and inequalities which are active. Yeah. No, for testing whether or not it's a cone, I will always this question mark when I ask, I'm going to choose alpha to be positive. Only then it's in the definition of cone. Which limit? The limit is only coming from here, from k tending to infinity. I won't do that. Okay. Right, but keep in mind one thing. When I choose Tk, I have these two properties that Tk should satisfy. Tk should tend to 0 for large values of k, and Tk should be positive. So I cannot choose a negative Tk. So at that point I would stop and flip the sign. Okay, so then I don't run into that issue. Fine. Is that clear to everyone? Okay. So active set everyone knows, equalities and inequalities which are active. So given a feasible point X and the active constraint set, okay, we say that LICQ holds if the set of active constraint gradients. So what are the active set? These guys, grad Ci, these are the gradients, and of course I belongs to the active set, is linearly independent. Okay, so I'm just making a statement over here to define what I mean by LICQ. Okay, So we'll just go step by step. So LICQ simply is linear independence constraint qualification. What does it say? When do I say that does LICQ hold? It's a yes no question. How do I answer it as yes no? At a point x where I am, I look at grad Ci for all the constraints which are active. What are the constraints that are active? Equalities are always active. Some inequalities may be active. I look at the gradients. Now gradients is going to give me, for example, in the example that I have, a gradient is a two-dimensional vector. For all the gradients, I will have a bunch of two-dimensional vectors. Can I investigate whether or not this set is linearly independent? Yes, I will get a yes or a no answer. If the answer is yes, then we say LICQ holds. If I get no, we say LICQ doesn't hold. Okay, so this is just a definition. We are going to do something useful with this definition in a moment. Okay, I run out of pages. Okay. Yeah. I mean, if there are more constraints than the dimension, then you can immediately tell. Okay, so what do I do with this LICQ business? Let's scroll up. So this is sort of the main thing that we are heading towards, the relation between algebra and geometry, right? So let's say let's write this down: algebra and geometry. This is our casual way of putting it. Algebra I'm going to call as, what do I mean by algebra? Linearized feasible directions. What do I mean by geometry now? Tangent cone, exactly. Okay. So the following are true statements. The tangent cone is a proper subset of the linearized feasible directions. Remember, we had given it a fancy F symbol, right? So that's this guy. So I won't prove it, although the proof is quite easy. The tangent cone is a subset of this. This is not the very interesting. The very interesting thing is this: if LICQ holds, then these two are equal. The tangent cone becomes equal to this the set of linearized feasible directions. In other words, if this LICQ holds, algebra and geometry will give me the same picture, which is what we were after. Okay, so this is, I think, Nosedal and Wright has this, in fact, as a lemma, 12.2, if you want to look at the proof. But I mean, this is really what you want to check. That if LICQ holds, the tangent cone and the set of linearized feasible directions agree. And having sort of written this without proof, let's go back to our example where we had that problem and see, does this help us out? Okay. So what did we have earlier? If you remember, our constraint was C1x was x1 squared plus x2 squared minus 2 equal to 0, and C1 dash x was this whole thing squared equal to 0, right? That was what we had. When I had C1x like this, what did my set of linearized feasible directions turn out to be? Does anyone remember? We use the definitions of 0 comma d2. This is what I had got, 0 comma d2. Okay. When I chose this guy with the whole squared, what did my set turn out to be equal to? Right. So, oops, this turned out to be d1 comma d2. Right. What did my tangent cone at that point turn out to be equal to? We just computed it. This turned out to be 0 comma d2. Right. Now, what was grad C1? Does anyone remember? So in this case, in the case of C1, grad C1, so you can calculate grad C1 over here. Grad C1 in this case is going to be 2x1, 2x2. So when I substitute minus root 2 comma 0, what does grad C1 turn out to be equal to? Minus 2 root 2, 0, right? And in this case, when I calculate grad C1 dash, what do I get? Whole thing squared, I take the gradient, what did I get? 0, 0. Okay. Now this is a little bit of a funny thing to ask. What do I say if I give you a set of n vectors and ask for them to be linearly independent? What does it mean? So I give you a set of vectors v1 to vn and I ask you what is the definition of linear independence? So we will say what? Alpha I vi equal to 0 happens only when all alphas are 0, right? Now this summation I went from 1 to n, right? Now supposing I make n equal to 1, it's legit. So alpha 1 v1 equal to 0 should happen only when alpha 1 equal to 0. That's the meaning of linear independence for a set of one vector. Now this is my set of one vector. Minus 2 root 2, 0 is in one set. Is it a linearly independent set? It is, because the only case in which alpha 1 times grad C1 equal to 0 is going to happen only when alpha 1 equal to 0, right? So this passes the LICQ test. This vector 0 comma 0, alpha 1 grad C1 prime will be equal to 0 for any value of alpha, including 0. So this set of which consists of just one vector, this is not linearly independent. So it's funny to talk in terms of just one vector, but it's correct, right? So this does not satisfy LICQ. Now when it did not satisfy LICQ, we can see that we should not expect the tangent cone and this linearized feasible directions to be the same, and that's correct. The tangent cone is telling me this, and it's only agreeing in the case where LICQ holds. When LICQ doesn't hold, we don't expect it, right? So see, very neatly we've managed to tie together something from geometry and something from algebra, right? Yeah, it is a little funny that our summation boiled down to just one term, but once you get past it, you can see linear independence. Any questions on this? Okay. So I want to mention that LICQ is one type of constraint qualification. In the literature, there happen to be several other different ways of constraint qualification, but in this course we are going to talk about one of them. Okay. And you notice that in terms of programming or coding, this is not something very difficult to check, right? If you wanted to check whether or not a set of vectors is linearly independent, how would you do it via code? You can put all of those vectors in a matrix and look at the rank of that, right? So it's easy enough for you to implement and check whether or not LICQ holds, right? If LICQ holds, what is the great advantage? I mean, you can look at all of this and say big deal. How does it help me? It helps you because I don't have to start constructing tangent cones at every single point. Constructing tangent cones seems to be a lot of work, right? First get a feasible sequence, then get a limiting direction, then put all of them together. Whereas if I know that tangent cone equal to linearized feasible set, to get linearized feasible set, what do I need to do? Just half spaces, right? I mean, grad C1 transpose D equal to 0, greater than equal to 0, whatever, right? So it's relatively easier for me to come up with a direction, right? So in most cases, that is the easier thing to work with rather than tangent cones. Okay, but the thing that will not fail you is tangent cone, right?